All right, in this video, I'm going to actually lay out quite a bit of information, so I'd encourage you to write some of this stuff down. We're going to talk about something called absolute maximums and absolute minimums. I'm going to lay out a theorem here, and then I'll do some various examples as we go along. I'm also going to lay out quite a bit of vocabulary, so let me start out with this, a little bit of vocabulary here. An absolute maximum or an absolute minimum. This is one of the easier vocabulary terms that we'll learn this year because it's pretty much exactly what it sounds like. If I needed to define these are the absolute max or min, finite y values. So we can't have an infinite absolute max or min. But it's the absolute max or min finite y values that f of x reaches, or that a function reaches on an interval. Okay. So if I had to draw just a little picture right here, most of these terms will make sense when you draw a picture. If we had some sort of picture that looked like this, we would say that if this was our interval from A to B, we would say, well, along the interval from A to B, here's my absolute max at whatever that y value is, and here's my absolute min at whatever that y value is right there. All right, so with that in mind, there is a theorem that corresponds to absolute max or absolute mins. As is the case with a lot of theorems in calculus, there's obviously a lot of math behind it, but the theorem itself is fairly straightforward and fairly common sense. So this theorem is called the extreme value theorem. So there's three main theorems that we need to be really comfortable with when the AP test rolls around. It is the extreme value theorem, and then two other ones that we've talked about, the mean value theorem, which we just recently discussed, and the intermediate value theorem. And I will obviously review a lot of these as we get closer to the AP test and as we move along throughout the year. Well, let's define the extreme value theorem, and we'll talk about some cases of it. So the extreme value theorem, as is the case with the intermediate value theorem and with the mean value theorem, the initial condition that must be met for this is that f of x is continuous along the closed interval from A to B, and I'll talk about why it's important for it to be continuous and why it's important for this interval to be closed in just a moment. But if f of x is continuous along the closed interval from A to B, we can say then it must have an absolute maximum and an absolute minimum along the interval. Okay. And if you just try to visualize this, again, as is the case with a lot of these, if you draw some sort of picture to understand what's going on, this will make sense. If I just pick 2 points in space and I draw something that's continuous between the 2 points, I am guaranteed to have an absolute max and an absolute min along this interval. Okay. In this case, this is continuous. Here's an absolute max, and here's an absolute min right here. And some students might say, well, does that have to occur at only one point? Not necessarily. I mean, even if I had a closed interval that was just a straight line, this has an absolute max and an absolute min. It just happens to be the y value for the absolute max and the absolute min is the same, and it hits it at every single point. But it does have an absolute max and an absolute min. So as long as I'm continuous between 2 points, I must have a highest value and a lowest value that I reach along that interval. Now, a couple questions here. Why does it matter? Why does the interval have to be closed? Okay, meaning we can't leave the end of the interval open. Well, let's draw a little picture here. If I drew an interval that looked like this is not a closed interval because we have a gap at the beginning value, and there's no absolute min because we don't actually touch that point right there. So if this was not a closed interval, it's not guaranteed to have an absolute min. It could have an absolute min, but it's not guaranteed to have it because you could have where the one of the endpoints would be the absolute max or min if it was filled in, but it's not. So it has to be a closed interval. And then the next question would be, why does it have to be continuous? Well, what if I drew an interval that was closed? So we'll say we have closed points here and here. But let's say that up at the very top right here, it was not continuous and there was a gap. Well, if that was the case, this would have no absolute minimum. Okay, or sorry, not an absolute minimum, but no absolute maximum up here at the top. So I'm not saying that if it's not closed and it's not continuous that it's not going to have an absolute max or min, but what I am saying is that this is a guarantee of existence theorem. So it's saying as long as it is continuous, and as long as the interval is closed, it has to have an absolute max and an absolute min along the interval. So quick question here, because you will see these every once in a while. Could we apply the extreme value theorem to, just pick something very simple here, f of x equals x divided by x minus 2 along the interval from 1 to 3. Okay, you don't really have to do any super calculus math on this one. Just looking at this, I would have to say that this thing is not continuous at x equals 2, because if I tried to plug in x equals 2 into this function right here, I would divide by 0. And since x equals 2 is inside of this interval, we would have to say, therefore, no, because x equals 2 is not continuous. Or I guess we could say, if we wanted to word this a little bit better, we'd have to say no because f of x is not continuous at x equals 2, which is within the interval. So if I'm not continuous somewhere along that interval, I am not allowed to apply the extreme value theorem. However, as long as I am continuous along the interval, I can apply the extreme value theorem. So if instead of 1 to 3, this said something like, I don't know, from 6 to 10, I could apply the extreme value theorem in this case because 2 is not inside of that interval. And I can only look at, I could just look at the beginning at 6 and the end at 10, and I could see, do I have an absolute max and an absolute min. However, as long as there's any space where I'm not continuous along the interval, I am not allowed to apply this extreme value theorem. All right, a little bit more vocabulary here. And we will culminate all of these notes with a concluding example at the very end, but a couple more examples in between here. So some more vocabulary. We have something in calculus called a critical point. It's a super important vocabulary term for later on, especially after we get back from Thanksgiving. So a critical point is any x value along the domain of f of x where f prime of, and we'll say for this, any x value, we'll call it x equals c for simplicity purpose. So any x value x equals c along the domain of f of x where f prime of c is either 0 or f prime of c is undefined. Okay, so any place where we are is equal to 0 or we're equal to undefined. And we can kind of think about this here. What would it mean for the derivative of something to be 0? Well, it means that at that point in time, the function is flat. So it would be flat, and then if the derivative is undefined, it means that at that particular point in time, the function is vertical. So I guess if I was drawing like some pictures right here, this point right here is a spot where the derivative of the function is 0. And then if we had, this second occasion doesn't happen very much, but if we had some sort of function where like we had one point in time where the slope of the tangent line was vertical, then we would say, well, at that point, the derivative is undefined. A couple quick critical thinking questions here. Can we have a critical point, which I'm going to abbreviate CP, without changing directions? Okay, so can we have a critical point without changing directions? The answer to this would be yes. Give you a couple scenarios here. Let's say we just had a flat line. Well, guess what? Every single one of these points along this function right here is a critical point because all of these have derivatives of 0. I were to draw a tangent line anywhere on this, the derivative would be 0. However, I'm never changing directions, so I just have a bunch of critical points without a change in direction. Then another scenario is I could have something where I'm increasing and then I stop increasing for just one particular point in time, and then I start increasing again. So we would have maybe a critical point right here without a change of direction. Okay, and we'll talk more about the changing of direction as time goes on here. But real quick, let's try a couple of little examples with critical points. And again, we'll culminate all of this with a concluding example at the end. But let's look right here. Here's what I want us to do. Let's find all critical points of f of x. We'll do this for a couple different functions here. So let's say that we had f of x equals x plus 1 over x. Okay, so I want to find all the places where the derivative of this function is either 0 or undefined. Well, in order to do that, I got to begin by taking the derivative of this function. Okay, I'm going to think about 1 over x as x to the negative 1. That should make it pretty easy to find this derivative. So derivative of x is 1. And the derivative of x to the negative 1, I'm going to multiply the negative to the front. So this would be negative 1 times x to the negative 2, which would be equal to 1 minus 1 over x squared. Okay, so here's my derivative. Now, one thing that you'll notice here is this is undefined if x is equal to 0. Okay, however, what I would say is x is not in the original domain of the function. Okay, so this is undefined. The derivative is undefined. I don't know why I wrote f prime of c here. I apologize. F prime of x is 1 minus 1 over x squared. This is undefined if x is equal to 0. And I'm going to put, but x equals 0 is not in the domain of f of x. Therefore, x equals 0 is not a critical point, because in order to be a critical point, we have to be within the domain of the original function. Okay, so this is sort of a side note, but x equals 0 is not a critical point in the function. But in order to find critical points, what we could do is we could set the derivative equal to 0, and we can see, hey, can we solve for x? So let's go ahead and try this here. If I subtracted 1 from both sides, and then I can get rid of the negatives right here, and then I could cross multiply. So on a lot of these, we're going to have to do some algebra. So when we cross multiply, we get x squared equals 1. And then if I take the square root of both sides, I actually get two different answers here. I get x equals positive and negative 1. So therefore, f of 1 equals 0, and f prime of 1, or sorry, f of, I apologize, this should be f prime of 1 equals 0, and f prime of negative 1 equals 0, because what we noticed here is when we set the derivative equal to 0 and solved, we got those two x values. So what that should mean is that if I look at the graph of this, I have critical points at x equals negative 1 and x equals positive 1. And just to assure that, let's go ahead and look at this graph right here. If I look at the graph of this function, here's x plus 1 over x. I do notice that at these 2 points in time, x equals 1 and x equals negative 1, I get some critical points. Okay, I can see that at these 2 points in time on the graph, we'll go ahead and add these in right here. At these 2 points in time on the graph, I do get that the function is perfectly flat at those points, which means the derivative is equal to 0. Okay, so that seems to check out. Let's try this with one more, and then like I said, I have a concluding example to close all of this out. And I know I'm kind of throwing a lot at you here, but this is so that I don't have to teach on the day of class right before Thanksgiving, because I don't think anybody would want to do that. All right, so let's try this. We're going to do the exact same thing here. Let's look at f of x equals the cubed root of x, okay? And I want to find all critical points of this as well. Another way of thinking about the cubed root of x is x raised to the 1/3. So what I could do if I wanted with that is I could take the derivative of it. And if I took the derivative of this power rule, this would be 1/3 times x to the, and subtract 1 from the exponent here, 1/3 times x to the negative 2/3, which is the same thing as 1 divided by 3 times the cubed root of x squared. And so here's my derivative. Now, what you'll notice on this one is that This is undefined if, once again, x is equal to 0. Okay. And the difference on this one compared to the last one is that x equals 0 is within the domain of f of x. I could take the cube root of 0. That would be perfectly fine. So this is undefined if x equals 0. Therefore, x equals 0 is a critical point of f of x because, again, it's within the domain and it's a point in time where the derivative is undefined. And we would notice here that if we tried to set this equal to 0 and solve this right here has no solution. Okay, so basically there's not going to be any points in time where the derivative is equal to 0, but there is one point in time where the derivative is undefined. So we do have a critical point with this function. And just to kind of verify that and check this here, if I look at the graph of the cube root of x, what you will notice is that if I drew a tangent line at 0, we would see that tangent line is perfectly vertical. Therefore, f prime of x is undefined. Okay, so we do see that x equals 0 is a critical point of this function. All right, so there's a couple of examples of finding critical points. So we take our derivative, we look to see where is that derivative undefined. If that point is within the domain, then we count that as a critical point. And we also set the derivative equal to 0, and we try to solve for x. And if we can solve for x, then that gives us another critical point. All right, one other vocabulary thing here, and then we'll get to that concluding example. And so for our last little bit of vocabulary here, I'm going to talk about something called a relative max, and sometimes we'll call these local max or min. Okay, a relative or local max or min. So what is this? Basically, it's easier for me to show this by drawing a picture than it is anything else. So let's just say I drew this picture right here, and we had a function that looked like this. This point right here and this point right here are relative maximum or a relative minimum. So this point right here is a relative max, and then this point right here is a relative min. And another pretty easy way to describe these are peaks or valleys in f of x. Okay, peaks or valleys in f of x, or you could say it as it's a place where f of x changes directions. Okay, it's where f of x changes direction. So, key question here. So say key question. What is f prime of x at all relative max and mins? Okay, well, what you'll notice right here is if you drew the derivative, f prime of x, if you drew a tangent line at all these points, you'll notice that the tangent line is always flat. Okay, so if we were answering this question, what is f prime of x at all relative max and mins? F prime of x is equal to 0 at all of these. Okay, and if we wanted to extend that idea a little bit further, just to kind of see how all of this stuff connects, we would have to say, therefore, relative max and mins only occur at, well, we just defined this. F prime of x is equal to 0. That has a name. Relative max and mins only occur at critical points, because those are places where the derivative is either undefined or it's equal to 0. Okay, so we can only find these relative max and mins if we have found a critical point in our graph. Now, we could ask this question just to extend this just one little bit further. Are all critical points the location for relative max and mins? Okay, are all critical points the location for relative max and mins? Well, the answer to this would be no. And I've sort of discussed this earlier, but just to give you a really quick example of this, if I had a graph like this, if I tried to find the critical points of this, I would have found a critical point right here. However, at that point, the function is not changing directions. So because it's not changing directions there, that point is not a relative max or a relative min. So just because something is a critical point does not necessarily mean that it's a relative max or a relative min. we'll talk later about how to make sure that it's a relative max or min. However, what I do want you guys to recognize is that a relative max and a relative min can only occur at a critical point. All right, so last but not least, and this is our concluding example of today. And I'll pull this up right here. Let f be the function defined by, we'll paste this here in our notes. Let f be the function defined by f of x equals 3x squared minus x cubed. And it says, what is the absolute minimum value of f on the closed interval from 1 to 5 halves? Okay, so I want us to focus on this for a second. Where can absolute max and absolute min occur? Okay, and once we answer this question, well, the rest of this problem can be fairly straightforward, but let's just write some quick scenarios down real quick. If I was looking from here to here and I had a graph that looked like this, okay, well, we would say, hey, this relative min occurs this absolute min occurs at a relative min, okay? And remember, relative mins occur at critical points. So an absolute max or an absolute min could occur at a critical point. That's one place that this could happen. Okay. Now, another scenario here is we could have a point at A and a point at B. And we could just have, I don't know, let's just say a straight line. Another place where this relative min could occur, because in this case, relative min, I guess on this one I should say relative min and an absolute min. Okay, and at this place, this is our absolute min, and this is occurring at an endpoint. Okay, this is occurring at an endpoint. So if we were trying to think about where could an absolute max or an absolute min occur, well, it either has to occur at a critical point within an interval, or it has to occur at an endpoint. Okay, those are the only two spots where an absolute max or an absolute min could occur. So guess what? If we're going to test to try to find the absolute min of this function, we have to identify the endpoints, which that's easy, they gave them to us. But we're also going to have to identify the critical points, okay? Because if we can identify the critical points, then we can figure out where this relative max or this relative min could occur. So first things first, I'm going to see if I can find the critical point of this function. Well, in order to do that, I have to take the derivative of this function. So it would be 6x minus 3x squared. Okay, and to find the critical point, I don't really care about where it's undefined because well, first of all, this one can't be undefined anywhere, but also I'm not going to get a finite value if something's undefined, so that's not going to work. But if I set this equal to 0 to try to find any of the critical points, doing a little bit of algebra here, I could factor out a 3x. This would give me a 2 minus x. And then if I solve this, 3x equals 0 and 2 minus x equals 0, I would get x equals 0 and I would get x equals 2. Now, only one of these really matters for this problem because check this out. My interval is from 1 to 5 halves. So I don't really care about any x values that are outside of this interval. So this one right here doesn't matter for this problem. I'm not saying it doesn't matter at all, but for this particular question, this doesn't matter. The only one that I care about is x equals 2. So here's what I'm going to do. Remember, an absolute max or an absolute min is literally the highest or lowest value that the function reaches at any particular point in time along the interval. So I'm going to create a little chart right here. I'm going to put my endpoints, okay, and then I'm going to put my critical points. So here's my endpoints, and then I'm also going to put my critical point, and I'm going to test these with the function. We'll go ahead and write this function down again. This function was, so I don't have to keep scrolling here. This function was y equals 3x squared minus x cubed, okay? So let's go ahead and try these and let's see what happens. So when I plug in 1, 3 times 1 squared is 3 minus 1, so I get 2, okay? So that means I have the point 1 comma 2. Okay, when I try with 5 halves, this would be 3 times 5 halves squared is 25 over 4 minus 5 halves cubed. Well, 5 cubed is 125, and 2 cubed is 8. So I gotta do a little bit of math here. This is 75 over 4. I gotta find a common denominator, and that common denominator would be 8. So I'm gonna multiply by 2 up here. So let's see. That gives me 50 times 3 is 150 over 4 minus 125, or I'm sorry, over 8 over 125 over 8. This would be 25 over 8. Okay, so I have another point at 5 halves, comma, 25 over 8. Okay, and just noticing this here, 2 is less than 25 over 8, and I'm trying to find an absolute min, so it's definitely not going to be this one. And then last but not least, when I plug in 2, that was my critical point, I get 3 times 2 squared, so that's 3 times 4, minus 2 cubed is 8. Okay, so 12 minus 8 is 4. So that means my other point here is 2 comma 4. So really the only points that I care about for the endpoints and the critical points, I'm looking at these y values here to try to find out what's the absolute min. Well, absolute min here, the smallest value out of all of these is 2. Okay, so which means that my absolute minimum has to occur along this interval at a y value of 2. Okay, and that x value that has that y value of 2 is when we're at 1. And so to finish this out, let's just check this graph real quick. Okay, if I look at this graph, I went ahead and restricted the domain of this graph from 1 to 2 because that's all, or from 1 to 5 halves because that's all I really care about here. You'll notice here, here's my endpoint, okay, 1 comma 2. That's where I found my absolute min. That's what it looks like. Here's my critical point at 2 comma 4, and here's my other endpoints at 20 at a y value of 25 over 8. The absolute minimum occurs at this point, or along this interval, at the endpoint, my first endpoint of 1. That's where I found my absolute min. Okay. This has a name, this test that we just did. It's called the candidates test. We'll talk more about it, and I'll probably come up with an example to start out class tomorrow. But this candidates test helps us find the absolute min, max or min along any interval. The only points that we ever consider when we're doing this are the critical points and the endpoints. I know this was kind of a long video, but hopefully it made sense. And we will talk about some more of this stuff at the beginning of class tomorrow. And then we'll have some practice after that as we go into Thanksgiving break. Thanks, guys. Bye.